very good morning, everyone. Thank you for making it to the early morning session. And I'm Deepti Aggarwal. And I'm working with the Advanced Technology Group at NetApp. And this work is actually a joint work done by both Rukma and me. Unfortunately, she couldn't be here today. But what I would like to talk about today is with the operationalization of various new age workloads. AI, ML, IoT, video surveillance, et cetera, et cetera, et cetera. What are some of those data management challenges that emerge for the underlying storage systems that we as storage practitioners, that we as data architects need to be aware of, right? So not more than a decade back, data was mostly confined to a data center. There were humans sitting at computer screens, either manually keying in the data, or at the maximum, it was machine-generated data, like from, let's say, application logs or server logs. Well, that data still exists. But then, in addition, we also have logs like clickstream logs. Every 10 minutes that we spend on the internet is actually digitized information today. What all we click through is all digitized. IoT data, that's a huge chunk of data, both consumer as well as enterprise-grade IoT. Right? Social networking data, I don't even need to touch upon this one. We are all familiar with it. We all generate this data day in and day out. Media content in the form of images, videos, multimedia, et cetera, et cetera, et cetera. And then an important aspect is that we are somehow not comfortable with the idea of discarding any data. We want to just keep it forever, right? And so our archives are growing tremendously. They're growing, in fact, we are seeing an unpredictable growth in the archives. Then further, it's no longer sitting in a data center or in one place. It is mostly data in motion. It's moving between, say, your edge compute to your private cloud deployments, to local attached DAS, to public clouds, to hyperscalers, et cetera, right? And then what you see on the extreme right of the screen is basically various pre-processing or processing activities that we do as part of AI ML routines, right? So we want to filter the data, we want to clean it, then process it, analyze it, build models around it, train our neural networks on it, and visualize it, and so on. The list goes on. So it's no longer just a read-write. We just don't write the data for us to be able to read it later. So in essence, what I'm trying to put across here is that the entire data lifecycle is actually changing. Right from the kind of data that is generated, to the way it is generated today and who is generating this data, to what we do with that data. Well, the whole meaning of the term processing has changed over this past decade, right? And then the whole paradigm about extracting value from data. Today, at any given point in the life cycle of the data, we want to extract as much information out of it as possible, right? And their business is built on just extracting value from data, right? And in the context of this new data lifecycle, new data pipeline, it somehow mandates the need for us to take a relook at the data architecture which is emerging, at the new evolving data pipeline, and how the data is flowing in this new world, right? And one way to look at this or understand this is to think of an edge core cloud kind of a pipeline. So let me just explain this a little bit. So starting from the extreme left, so edge. Edge is a compute or a storage presence very close to the point of data generation. This is where all the raw data from the endpoints, the data endpoints, is actually collected, and it's the first point of data ingestion into this pipeline, right? And but it's no longer just a dumb storage. Here is where we want to take real-time local insights and derive some model inferencing. So for example, let's say we have a video surveillance, border surveillance video stream that is coming into our edge node. Now, as soon as we see some sort of anomaly in that video, we would want to alert somewhere, some security down the line, right? But that decision and that intelligence of finding out that this is an anomaly and this is different from usual behavior, those are the kind of local insights that we want to derive at the edge. Right? From there, the data moves to core. So think of the core as your traditional data center, which is a very secure, protected environment where all your AI and ML model training happens. Right? From there, of course, comes the cloud. While it is the last spot for our data in terms of the long-term data retention value that we want to derive, but also it is where we run various analytic applications today by leveraging the umpteen as-a-service solutions hosted out there, right? Now, an important point to note here is that these boundaries between the edge, core, and cloud, they're not very strict. It's a very fuzzy kind of boundaries, and it's a spectrum more than a distinction, right? While some enterprises choose to follow an edge core cloud, some others do follow an edge cloud or an edge core kind of model, right? So now what I would like to do is bring up some of the key data management challenges which I think are important in this new world. So if you read through this list, performance, efficient storage, security, compliance, data quality, these are all terms which we are familiar with. It's not that I'm introducing a new data management challenge which has suddenly emerged. These are still the old ones that we have been dealing with, but they need a rethink or a re-architect or a new look in the perspective of this new data pipeline and new data model, right? So perhaps the only sort of new word around here is data quality, right? So why is quality important? Well, in the ML world, there's a common saying that if you feed junk into your model building, what you will get out would also be junk. So it's really important to establish that the data that you're feeding into your AI ML routines is actually qualitative data, right? Okay, so now let's look at each of the edge core clouds in further detail and the specific management challenges or issues that we need to take care of in all these three, right? So edge, as I mentioned earlier, it is the first point of data entry into the pipeline. It is where real-time insights are derived. And this is also the point where the data needs to be transferred over WAN to the core, right? And whenever we talk about WAN transfers, we talk about costs. So costs in terms of both dollars as well as the network bandwidth. So of course, a natural management challenge there is ensuring that we do something about storage efficiency over the wire and transfer data so as to reduce or optimize on network costs as well as dollars, right? So now there are two views to this that practitioners have. One is that we should actually transfer only the limited amount of data. So basically only transfer the so-called useful information. So anytime there is a deviation from normal in the data stream, that is when my data becomes interesting. And that is when I should be able to, that's the only time when I should transfer data. And of course, this gives me a huge data reduction. But then another contrasting opinion is that I don't want to discard any data, transfer everything. But at the same time, I want to optimize on my WAN transfer costs, right? So there's a trade-off there. But what these people are okay with is if we can get to some sort of data approximation, right? So maybe let's say a value of 10.05 for a particular sensor, if I can approximate it to 10, but that gives me a huge data reduction, then I'm okay with that because it's still a quantifiable error bound, right? So And in fact, there is interesting research happening to in this area, more focused on time series for minimizing the data transfer that we do from edge to core, right? So very quickly, so the red series that you see there is the actual time series of, it's some example of a seismic time series out there. And the blue is what is called the matrix profile. It's a research work being done by a team in University of California, Riverside. And so the basic concept is that anytime there is a repeating pattern, for example, in this red time series, the 2 peaks that we observe, right? The matrix profile value for that repeating pattern would be very low. So in essence, matrix profile helps you identify repeating patterns in a time series. And hence, any time series just becomes a sequence of repeating patterns. And hence, it automatically leads to data reduction, right? There are certain other benefits which are listed on the slide, like in terms of it being an anytime algorithm, its ability to scale with hardware, and so on and so forth, which make it even more suitable for edge computing, right? So this is just to highlight that indeed it is an important problem, and there is research happening in this area supporting or moving us in that direction, right? Now, another important aspect that we should definitely be involved in at the edge is about metadata enrichment, right? Why at the edge? Because it's the first point of data entry. This is where we have the maximum information about the data. From here on, the data gets transformed, processed across multiple processes, it flows down the pipeline, it gets modified. But at the edge is where we have the raw data, the most information about the data, right? So what are those kinds of metadata tags that I'm talking about? So let's talk about data quality a little bit more. So as I said, it is indeed difficult to quantify quality, right? But there is work happening in terms of defining various metrics which help us quantify quality. Some of those are listed here. For example, completeness. So is my data complete? Now an edge node possibly receives data from not million is probably an exaggeration, but hundreds of different endpoints. Now, how do you ensure that I have indeed the complete data? Have I received all the data for all the timestamps from all the sensors? Right? That is one measure. Accuracy is another one. So sensors might go bad. They might still keep sending me data. How do I ensure that it's accurate data that I'm receiving? People deploy multiple redundant sensors at important places like oil rigs to take care of the accuracy, right? They essentially just redundant sensors recording the same thing just to take care of accuracy, right? Timeliness. So what I'm receiving from sensors is actually just data streams. There's no timestamp associated quite often with them. So how do I make sure that I am receiving the timestamp T1 from all the sensors at this point in time? Are the transfer speeds the same? So those are, basically these are some of the ways in which we measure data quality today. And there is research happening into arriving at more ways to measure this. Then the kind of data, whether it's an image, whether it's a document. If it's a document, is it a financial document? Is it a legal document? What is it? What is this blob of storage that I'm getting? The behavior of data. So I touched upon this earlier, but is it normal data? Is it the normal expected behavior of the data? Or is it something that is different from normal? And if it is different from normal, can I categorize it into saying class A different and class B different and class C different, right? The lineage and auditing, this has become more of a compliance requirement today. We need to maintain data about every modification or every process that is done on the data, right? So of course, there's the lineage auditing data. Now, how does this metadata help us? Sure, it's enriching the data, but how do we use it? So it aids in various data workflows down the pipeline, right? Maybe in the edge or in the core. Let's say if I have been able to tag images as, say, X-ray images of brain scans, right? Now, in my archival tier, it might be useful for me to place all these brain scan images in one container so that I can get the maximum deduplication out of it, let's say, right? So and this information about it being a brain scan image is best added at the edge, right? So that those are the kind of data workflows that this can potentially help in. And of course, tools like Kafka and Spark Streaming, which are mainly used for the purpose of stream analytics today, they have realized the importance of custom metadata, and they have added this support in their tools, right? So it's out there for us to go and leverage. Another major concern at the edge is the security. So there are too many endpoints that an edge system has to deal with. And the more the number of endpoints, the more vulnerable the system is in terms of security attacks. There are mechanisms, the traditional mechanisms of access controls and perimeter security in the form of firewalls, which are added today in the edge systems. But then we also need some sort of authentication from each sensor to the edge node. But then again, the problem does not end there, because we need to be worried about data integrity, yes, but also device integrity. How do I know that the device, the endpoint, has not been tampered with? How do I know that it has not been pulled out from one autonomous vehicle and pushed into another autonomous vehicle? Right? So those are important security concerns. One way people have dealt with it is to look at SSL certificates-based session boundaries, which is based on public key sharing. So I'm not a security expert by any means, but what I'd like to highlight is it is an important concern, and we definitely, as storage people, need to worry about this one and figure out a means of achieving good security, right? So coming to the core. So core, as I said, it is a secure domain, protected environment where we have, where you can think of it as your traditional data centers or private cloud deployments, mostly dedicated hardware. This is where most of the model training meaning the neural network model building, the ML model building, and all the AI activities happen here, right? And the moment I talk about AI and ML, what comes to mind is performance. So why is performance so important in terms of AI and ML? So there are today many neural network variants. And then it has become very easy for anyone to go ahead and build a neural model today, right? There are these platforms like TensorFlow, Keras, Theano, which has abstracted out all the mathematics behind these models and presented to you very easy to use APIs. The data is no longer a problem. The infrastructure in terms of GPUs have become very easy to procure. It's become on the click of a button, really, to go and procure a GPU today. And all these factors have basically made deep learning networks, machine learning networks, very, very commonplace today. And they demand high predictable performance from the underlying storage. With such massive parallel compute as a GPU, the storage requirements, the performance requirements from storage are also very high, right? And these model training, by the way, stretches into days. So a small factor slowdown in the performance that storage can provide actually has a huge impact on the round time for the machine learning training and so on, right? Now, a traditional way that we have handled performance as part of the software in storage systems is through indexing. So think of a typical RDBMS. If we always query the data by names of people, what I would do is essentially just go ahead and build a index on the name field in my database, right? But then I have the word smart added there, right? So why smart? Because my workloads are changing. Today, I might be interested in looking at all the anomalous data that I have received, say, from the Asia Pacific region. But then tomorrow, I might be interested in looking at all the temperature sensor data across geographies. So the kind of indexing requirement both these queries have from the underlying storage to serve them efficiently is very, very different, right? So decisions regarding which columns to index and then when to update the indices. So remember, this is a continuous stream of data that we are talking about. So at any given point in time, we have added new data into our system. So there is a need to update the index. But then updating the index involves sufficient compute cycles. So there is a trade-off there. How often do you update the index? Maybe for some, you might want to update it real time or near real time. While for some others, you might be okay with the 1 hour periodic frequency, let's say, right? And then often, we forget about deleting indices. But then, we want to ensure that we identify which indices to delete based on when they are not in use. Why unnecessary spent compute cycles in updating indices we no longer use, right? That is one way in which smart data indexing can help these AI/ML workflows. Another way is what is talked about in this paper. The link is on the right. It's called learned indexes, right? So let me try to help explain this with an example. So let's say if you were storing integers from 1 to 50 in any storage system, right? And now I want to index this data. What I would do is build a B-tree index on this. And the moment I want to query, let's say a number 26, it will take me log n operations to give me the data. But what is that property of data which it has not utilized is the sort order or the distribution of keys. For example, I know that 1 to 50 is a sequential data, and if the value 1 is stored at offset ABC, the value 26 would be stored at offset ABC plus 26. I don't need to go through audio login operations. So that is what this paper really talks about, where it says that if we can learn the structure of keys or the sort order of the keys, then it can help us save time in terms of just going through the index. Right? So if you notice, by the way, this is trying to build a ML model to solve some of the core data management challenges to help AI/ML workflows perform better, right? Yeah. So moving on, core is also the point which has to deal with the complexity of big data, the volume of data, receiving multiple data streams from multiple different sensors, the variety of data. It's no longer just integer or floating point numbers. text, multimedia, structured, unstructured, all kinds of data. The velocity of data, it's continuously real-time, near real-time data that we are receiving. And then there are various processes which are done which operate on these streams to generate even more streams, right? So all the 3 V's of the big data are in action, and in such a complex scenario, it becomes a challenge to even provide a holistic view of this data to the end user or the application. The other aspect which we need to deal with is preparing this data for transfer to the cloud. It is going to outside my private domain, my secure environment. So what is it that I need to do before I can send it across? Do I need to mask out PII information? Should I anonymize my data? Which pieces of data should I bundle together? Should I encrypt it? Should I compress it? Should I deduplicate it? What should I do with this data before I can even send it to the cloud? Right? So that whole packaging of data and preparation for transfer has to happen here. So let's say our data has reached the cloud, right? It's a less trusted domain, one of the primary functions being data archival. And today, compliance regulations is what is governing the life cycle of the data or the data archival requirements, right? For example, if you look at regulations like GDPR, they have an important clause called right to be forgotten. So what it mandates is that any user should be able to come to the system and say that I want to be forgotten from the system. So basically, remove all documents which are associated with me, with that particular user. So now imagine the kind of metadata that we need to incorporate into our data streams to be able to serve this query. Forget about efficiently, but just to know that these are all the documents associated with a particular user. Imagine the kind of metadata that we require, right? The provenance and traceability is, again, something that we have to maintain, and we have to make sure that we do efficient indexing on or efficient means of retrieving the provenance or the lineage of a data stream. And of course, long-term data retention also comes as part of compliance regulations. And most often, this is the coldest and deepest archives for enterprises. And it's mostly an overhead for them, right? Because this is not data that they're using day in and day out. But just to meet the compliance regulations, they need to be storing it for a long period of time. And the cost associated with that in the archival tier, of course, goes up. Now, various hyperscalers today have their own way of dealing with the cost. They have introduced what is called archival tiering. So basically, let's say we have an AWS example here. Even within S3, there are multiple tiers of archives, which have a trade-off between the retrieval times and the dollars per GB involved, right? And then in archives, we most often want to use erasure coding over replication to minimize on the cost. The idea is the same. We just want to reduce the cost in the archive tier. But then there is another way to minimize this cost even further. So if we are all aware that there are various erasure coding schemes which have different trade-offs between storage overhead, the network bandwidth, the read times, and the compute performance, right? So maybe for your active archives, you might want to use an erasure coding scheme which gives you lower read times. But for your coldest and deepest archives, you might want to use the erasure coding scheme which just gives you minimal storage overhead. You're not bothered about anything else but the cost when it comes to your lowest tier of archive, right? So that is one way of minimizing the cost even further. And then coming to data security, which of course without which any cloud talk is not complete if I don't talk about data security. And the way people have dealt with this, or enterprises have dealt with this, is they store encrypted data in the cloud, store the key metadata server on-prem in a protected environment, and establish what is known as VPNs or VPCs to provide restricted access across the data center and the cloud, right? But what if now I want to run analytics on archives? Because I want to derive value, right? I don't even want to leave my archives to derive value out of data. So what if I want to run analytics? Because my data is encrypted, how do I even make sense of this data in the presence of encryption, right? So, well, there is ongoing research work happening which have tried to arrive at encryption schemes which compromise on some aspect of security to retain a property of data. For example, there is order preserving encryption. So let's say my analytics algorithm is interested in only knowing whether the value A is less than value B. I don't really care about what is A and what is B, but all I'm bothered about is the order there. So that is when something like order preserving encryption could be useful, because with that methodology, I can still retain the order in the data while encrypting it, right? So those are some of the dimensions of interest which come up when we talk about this new age workflows or new data pipeline or the evolving data model, right? But there are some other dimensions which I haven't touched upon in this presentation. However, they are equally important, right? For example, storage infrastructure suitable for each layer. So whether the edge computing requires a key value pair, whether it requires a traditional NAS, what is that storage infrastructure which I require at each of these stages of the data lifecycle, right? The implementation of compliance regulations. So that is again something which is becoming more and more important today. First, identifying what documents need to meet with which compliance regulations. Let's say I know I want to comply with HIPAA, but what are those documents which I know should comply with HIPAA? How do I identify those documents? And then even if I have identified them, how do I implement those compliance regulations? And if I've implemented them, how do I ensure that I am meeting with the regulation? What is that validation feedback which can be provided, right? So the compliance is a whole together different ball game in some sense, right? Then the idea of a global namespace across this pipeline. I do not want the user or the application to say that from node 10 in your core database, can you provide me this information? The idea of a global namespace has to come up, and we need to provide a coherent, consistent view of the data across this entire pipeline, while abstracting out where in the pipeline is the data existing, right? So in the end, I would like to leave you with a few key takeaways. So we talked about the changing data lifecycle, and we talked about the fact that though the data management issues remain the same, they need a rethink and need to be re-architectured in the context of these changing data workflows. We discussed a couple of performance, compliance, quality, security, and storage related challenges, data management challenges that come up, right? So that's all I had. I can take any questions.